All right, this is lecture 8. I'm assuming you all watched the recordings last week of P and NP and EXP and all that. Last time I taught this, there was a little bit of discussion about P versus EXP, so that's why I made this lecture. Okay, let's talk about it. Polynomial functions is a made up of terms that are only added, subtracted, or multiplied. So if you see anything beyond addition, subtraction, or multiplied, it is not a polynomial function. It's an exponential or something else. Okay? So polynomials are sums of variables and exponents expressions. Polynomials are algebraic expressions that include real numbers and variables. Division and square roots cannot be involved. Variables can only include addition, subtraction, or multiplication. So here, these are examples of polynomial expressions. You can have exponents, you can't have division now. Okay. So these are no division. Okay. These are just examples of polynomial expressions. Okay. Do you need to know that for this? Not really. I just thought it was something important y'all should know. Okay. EXP functions, on the other hand, they use this exponential because of the non-integer values. We could get into all kinds of other ways. They include division. Okay, this one here has a 0.5, so it's not a real number or not a whole number. Or any problem that can't be solved in polynomial time, such as the knapsack. You learned about the knapsack, how the knapsack is the correct combination of items to make the total work. Okay, hopefully you all watch those. Okay. Now, are you all watching prior years as well? They're pretty much the same, but I do explain them a little bit different every now and then. Now, with the knapsack, it says, would take forever to try to figure out every combination for a simple knapsack that are 2 to the 200th apart. Well, the Merkel-Hellman knapsack, no, it's Diffie-Hellman. Where's Merkel-Hellman? Diffie-Hellman. No, Diffie-Hellman's the key exchange. So it's Merkel-Hellman knapsack then. Is it Merkel-Hellman?
It's Merkel-Hellman.
Okay, Merkel-Hellman. Okay, it's good mayonnaise. Okay. So, with the Merkel-Hellman knapsack, imagine having 200 numbers, where each number is 2 to the 200th apart from the prior numbers. In our examples, we use numbers like 1, 3, 5, 11, and 7, and something like that. But that is 2 to the 200th. So even if it used a 1, the second number has to be greater than that. So those are some very large numbers. So when we get into RSA soon, we're going to do examples of using very basic small numbers, but in the real world, they are crazy huge. Okay. Yeah, if we were doing encryption using 1, 3, and 7, I mean, there's no sense. Why even waste our time? Okay. There's some other functions. One-way function is a popular one. One-way function is what we use for our passwords. When I logged into the computer here a few minutes ago, I typed in my username and I typed in my password. Did it send my password across the network? No. What it did was it encrypted my password with MD5 crypt or whatever. I think we're using MD5 crypt on these. So it encrypted it into a hash value, sent that hash across the network, and then on the row state server, it's stored that way. It's stored as a hash. That way, if you ever call the help desk and say, hey, can you tell me what my password is? They can't because they can't decrypt it. It's kind of like here. If you broke a windshield into a million pieces, could you ever put it back together again? You can shatter it. You can't unshatter it. Same with password hashes. You can create the hash. You can't unhash it. So the people ask, how do we break passwords? Well, if they're stored in a hash value, like we're going to be using, at least in forensics, a program called John the Ripper. Some of you have already used it. What John the Ripper did was it calculated hashes. So it took the word apple, ran it through the MD5 crypt algorithm, and came up with a hash. And then compared the hash of apple with the password hash it was looking at. If they match, it's like, got it. It didn't decrypt that hash. It can't. Now, older versions of Windows actually stored it in reversible encryption. A lot of programs still do. QuickBooks stores it in reversible encryption. There's actually quite a few of them that do. So, zip, if I remember right, plain zip, not 7-zip, plain zip, I'm pretty sure stores in reversible encryption as well. So that's what a one-way hash function is. Okay. Here's what MD5 looks like. Okay, I took a word This is a super secret message. I ran it through an MD5 hashing algorithm, and I got that word at the top. Okay? Now, should any other word, message, whatever, produce that same hash? We would hope not. If they did, it would be called what's called a collision. That's a bad thing. That's like, can you imagine, if two keys open, two different keys open your car in the parking lot? That'd be a bad thing.
It has happened, Piper.
It has happened. And it's like our network cards. Our network cards have a machine code, a MAC address encoded on them by the manufacturer. We are producing more network cards than numbers. So what do? They reuse them. But what are the odds that a network card, from 5 years ago is going to be on the same network as a network card produced today? But it could happen. So collisions are not good. And MD5 actually has a weakness where they've proven you can make a collision. But it's so minuscule possibility, it's like it's not going to happen. So I took this message here. Now I capitalized the H. All I did was I changed one letter to a capital. And look what the difference is in the hash. It's crazy, isn't it? It's not even remotely the same. We learned, I think, 2 weeks ago that the results of a hash or the result of a cryptographic algorithm should be equal to the same size or smaller. We don't want it to be huge.
Second B is in the same spot. What that's it.
Yeah, there's not much of it at the same spot. So is anyone in forensics this semester? Can't tell you the secret 10. Be careful when you read hashes. Be careful. Some of you already had that class. Remember the hash you had to read? Okay, so that's the end of that one. So again, another very short lecture there.